Welcome back. We'll have a break of 3 minutes. Okay. Welcome back, everybody. This is the second talk of today. It's my pleasure to introduce Amaury Freslon from Paris. Please.
Talk about joint work. Yeah, it's blue. The blue light is on. Does it work? Maybe I should put it. Is that better? Maybe I could turn it off and then on again. Yeah, everyone here? Sound okay? Well. Sounds nothing. You want me to try just to switch it off and on again? Yeah, sometimes it works. Okay, I can't turn it off. So you don't hear me? No. Yeah. I can try again. Okay, does it work better now? Still not? Still don't hear me? Yeah, okay. Keep talking until someone hears me. Yeah, how's it going? You can hear me. Great. Is that okay for everyone? Yeah. Yeah, well, that sounds okay for everyone. Yeah. Okay, I'll try to speak quite loud. I can try that. Okay, so thank you very much for the invitation. And I'm going to report on the joint work. Let me say this right away. It's a joint work with Symmetry and streaming. Wow. Okay, and I'm going to talk about a part of this work, which is about quantum symmetries of classical spaces. What do I mean by this? Well, you've all heard about non-commutative geometry and the underlying idea, which is to consider some non-commutative algebras as substitute for geometric spaces when some properties kind of make the topology crack down for a reason or another, for instance, for foliation, things like this. So as soon as the idea of considering these non-commutative, for instance, C-star algebras as spaces arose, one natural question which came up was, what can be the symmetries of such a space? So of course, if you take a C-star algebra, it has a group of star automorphisms. But, well, since we've managed to upgrade, say, topology or geometry to a non-commutative world, why don't we try to upgrade symmetries also to this non-commutative world? And at the same, around the same period as the emergence of non-commutative geometry, there is a notion, another important notion that appeared, which is that of a quantum group. So that appeared in different contexts where there was some Hopf algebra that was somehow playing the role of a generalized symmetry of a problem. So when you combine the two ideas, you came to the question of, can Hopf algebras like be seen as symmetries of non-commutative spaces? And it turns out that there's a class of Hopf algebras which is particularly suited to this, which is called compact quantum groups. And these are kind of versions of Hopf algebras inside the setting of non-commutative geometry. So let me tell you a bit more precisely what I mean by a compact quantum group. So I'm going to talk about really non-commutative topology. So this means C-star algebras. And to simplify life, I will always consider unital C-star. So non-commutative compact space. So what is a compact quantum group? Well, it's a non-commutative compact space. So it's a unital C-star algebra. Let's take a unital C-star algebra. And we will think of it as the algebras of functions on an object that we want to call a compact quantum group. So as usual, we will write it like this, even though, of course, this bold G doesn't refer to any existing object, but it's just a notation to remind us that we think of this as an algebra of functions. Now, there is a general theory of how you put the analog of a group structure, but I'm going to focus on a special case, which is a bit simpler to describe, and which is the one that I will be interested in the remainder of the talk, which is called compact matrix quantum group. So how does it work? You have a unital C-star algebra, and you will assume that it has a specific set of generators. So it's generated by some elements that I will denote by Uij, and there are n square of them, which satisfies some conditions. So here are the conditions that I want. First, there will be self-adjoint. So I will say a word about that in a moment. Second, we will have some condition, which simply means that if you put them into a matrix, then that matrix should be a unitary matrix. But recall that they are self-adjoint. So that just means the matrix should be orthogonal, really. So this means that if you do this sum, then this should be delta ij times 1, and the same should work if you do this. Complete sum. Okay, so basically what I'm saying is it's a non-commutative space formed of orthogonal matrices. And n is it's an integer. And oh sorry, yeah, n is just an integer. You just fix an integer n. This will be the size of the matrices that we have in our non-commutative space. And now we need a group structure. So we need something telling us that that non-commutative set of matrices is somehow stable under some operation. And this will be condition 3, which tells us that there exists a star homomorphism delta from C of G to C of G tensor C of G. So all my tensor products of C-star algebras are maximal ones, just to not having to think about it, right? This is not important at all. Such that delta of Uij is given by the following formula. It's just the sum of Uik tensor Ukj. So you know that formula, of course, it's exactly the formula for matrix product. So the existence of that map should be something like saying that if you take two non-commutative matrices in your space and you make the product, this should again be in your space. So, yeah. It's, sorry? Yeah, they're self-adjoint, yes. Yeah, they're self-adjoint. So, no, it's really Uij. They're really self-adjoint, yes. Okay, so that's a formal definition. Now let me tell you what it means in the classical case, in the commutative case, to see where it comes from. So just take a group, but a group of orthogonal matrices, of course. So you take a closed subgroup of OM. So how do you see it as something like this? Well, just take the function Cij, sending a matrix to its ijth coefficient, right? So these are functions. Obviously, C of G is generated by these functions. Right? Yeah, put a square here. That's not, I mean, I and j range from 1 to n, so that's n squared generated. That's what I meant. So it's generated by this. That's just the Stone-Weierstrass theorem. So it's generated by this. And of course, that relation is satisfied because since we have orthogonal matrices, this means the coefficients are real. So if you define f star to be the function which sends x to the conjugate of f of x, then theCij's are self-adjoint. And that relation, of course, is satisfied just because all the matrices are orthogonal. So in fact, if you take the sum of these coefficients, this will always be delta ij times 1. So you have the conditions here are satisfied. So condition 1 is satisfied. It's generated by this. Condition 2 is obvious. And what is condition 3? What does that mean, that map delta? Well, in fact, you can do something. You see a map like this. So you want something from C of G to C of G tensor C of G. Now, it's well known that if you have two compact spaces and you take the tensor product of their algebras of functions, then this is exactly the same as the functions on G times G. And now when you have a star homomorphism like this, this is the same as a continuous map from here to here. So all I have to do is to give you the continuous map from G times G, from G times G to G, and that's just the product map. So if you take the dual of the product map, so this would be the map that sends the function f to the function f of gh, right? You see here, I have a function of one variable. I can build a function of two variables just by using the group product, the matrix product. So that exactly, and if you take for f the matrix C, the function Cij, then you get exactly that formula, because you just get the matrix product. So this is a thing that generalizes groups of orthogonal matrices, okay, compact groups of orthogonal matrices. So that is the objects that I want to look at. And the nice thing is that when you have this, then it can act on a C-star algebra. So what is an action of this on a C-star algebra? So we'll say that it's an action of G. So I won't say it again, but all C-star algebras are uniform. So it's a star homomorphism alpha from A to A tensor C of G. So once again, if everything is commutative here, then you can dualize that map, and that's just a map from G times X to X, which is what you expect for an action. And this should satisfy some conditions. So the first one is, if you apply the action map twice, then this should be the same as doing this. So if you dualize this, this is exactly saying that this is an action in the sense that if you let one element act and then another, it's the same as letting the product of the two elements act at once. Okay, that's really the dual version of this. And then you need another condition, which is something like this. So what does that mean? Epsilon is the map that sends Uij to delta ij. So it's a map from C of j to C, which plays the role of evaluation at the neutral element, at the identity, right? We have matrices, so the neutral element is just the identity matrix. It's the one with coefficients delta ij. So I'm just applying any function on that thing. So that gives me that star homomorphism for any compact quantum group. And I want this to be true, which means that the neutral element acts as the identity on A. And if you combine the two, then for any compact group like this, this will tell you that you have an action. Okay, so that's an action. And now the question is, if you have a non-commutative, commutative or non-commutative space, how can you study the possible actions of compact quantum groups on it? And in particular, do we have nice quantum groups acting in a non-trivial way on some spaces so that this would give us some information on the space? So you have to be a little careful because, of course, any quantum group acts on any C-star algebra via the so-called trivial action, where you just send any x to x tensor 1. So of course, having an action is not really an information. You need an action which is non-trivial. So what we want is to have some definitions, some notions for an action which guarantee that it's far from being trivial. And there are two notions that I will use in this talk that I will give now. So assume we have an action of a quantum group on a C-star algebra. So we will use two notions of being far from trivial for an action. One is to be faithful. So what does it mean to be faithful for a group action? Well, it means that the group homomorphism that you get from your action is faithful. So in particular, it means that you cannot factor it through any quotient, right? So if you have a quotient of G, right? So if you have a quotient of G, then the continuous functions of H become a subalgebra of the continuous functions on G, right? Just by composition. So faithful would mean that the action does not factor through a subalgebra here. So it's faithful if there does not exist some subalgebra here, such that first, that subalgebra corresponds to another quantum group. Right? So I'm just saying this is the analog of a quotient of G. So there's no quotient of G such that when I do the action, in fact, I get into that thing, right? So you see, of course, if you have an action like this, then you compose with the inclusion on the second tensor and you get an action of G, but that's a fake action of G. That's H, which is really acting there. So faithful means you don't have that kind of things happening. And the other condition is being ergodic. So ergodic means that some subspace, what's called the fixed points of alpha. So what is this? It's the elements in A such that when you apply alpha, you get X tensor 1. So these are the elements on which the action is trivial. So of course, if X is the unit, then it's in there. So ergodic means this is the only thing you have in there. So this is just C times 1. So you see, this is another. So this is a way of saying it's non-trivial because the trivial action is exactly the action which comes from the trivial subgroup, right? So you're ruling out anything like the trivial action. Here, that's another way of ruling it out. You're saying the only elements on which we can act trivially are just the unit and its multiple. Okay, so now.
Why you call this ergodic as opposed to like minimal or free?
Yeah, so thanks for asking the question. It's ergodic because this is equivalent to saying that there is a unique invariant state on H. And hence, classically, this means there's a unique ergodic measure for the action. So that really has to do with ergodicity, in a sense. Yeah, yeah, I think so, yeah. Okay. So now we have these notions. And so the question is, can we find, given a classical space, for instance, or a quantum space, can we find faithful actions of quantum groups, or can we find ergodic actions of some quantum groups, right? And we can in some cases, and here is the first and one of the most important examples. So it's due to, I'm going to give a definition of a quantum group, which is due to someone called Wang, but it's not Ximeng Wang. It's not the co-author. It's Shuzhu Wang. So he was basically working on the question of what are the quantum symmetries of a classical space. And he said, okay, let's start with the simplest possible space. That is just a space made of a finite number of points. Okay, you can't do simpler than that. And is there a quantum group acting on this? And he found one. And the quantum group he found is defined in the following way. So the quantum group itself will be called S n plus. And the algebra is the universal sister algebra generated by elements uij. Okay, so that's expected, such that first the uij's are projections, and they are even orthogonal projections. And second, when you sum them over a row, say, like this, then you always get one. And same thing if you sum over a column. Okay, so projections, and when you sum there over rows or columns of the matrix, you always get one. It's a kind of magic matrix. So this, in fact, satisfies all the axioms that were over there. So of course, the generators are self-adjoint. And what you can observe is that on a given line, these are projections. But when you add them, you get a projection. So in a sister algebra, this implies that they are pairwise orthogonal. And from this, you get that the matrix is unitary, right? If you compute sum of uik, ujk, well, they're on the same row here. So in fact, this thing is 0 unless I is equal to j, and then, well, then you sum them. Okay, so you'll get the result quite easily from this. And as for the delta,
there's a question in the
yes.
chat here. Can we realize the matrix uij as a permutation matrix?
So permutation matrices give you an example of this. Yes, but it's more general. So I'll say this in a second. So yeah, I can say it already. If you take the classical permutation group, okay, so you can see this as a closed subgroup of ON. You just look at the permutation matrices. And then you look at the maps Cij, which sends a matrix to its ijth coefficient. But for permutation matrix, this means you just get something like this. So these functions, they satisfy these conditions, right? This means exactly that they have value 0 or 1, and that in each row and each column, you have exactly one coefficient, which is 1. So that's a characterization of permutation matrices. So this means that you have a surjective star homomorphism from functions on Sn plus to functions on Sn, right? But this is bigger because this is non-commutative in general. Right? In fact, this is exactly the abelianization map. This is the maximal abelian quotient of this. And for the delta, well, you just use the universal property. So if you look at the elements, say Vij, which is sum of uik tensor ukj, you just check that they again satisfy these two things. And if they do, then by the universal property, you have a surjective star homomorphism sending uij to this, and then you're done. And that's a very elementary computation here. So this gives you a compact quantum group. This gives a compact quantum group, and it's usually called the quantum permutation group. Now, why is it called a quantum permutation group? For two reasons. The first reason is, as I said here, that its maximal abelian quotient is the algebra of functions on the classical permutation group. So it's a non-commutative version of the permutation group. And the other reason is that this quantum group acts on endpoints. So the algebra of functions on endpoints is just C to the n. And in fact, there is an action. So I'm going to call it alpha u for some reason that will appear later on. There is a map like this. And how do you define that map? Well, you take a basis vector here. So we take the canonical basis, call them E1 to En, and then you send it to the sum of Ej tensor Uij. Okay, and you can check that this is an action. So how do you prove once again that such a homomorphism exists? You just check that these guys satisfy the defining relations of Cn, and then you have a map. And if you try to look, you'll see that to define an action, you need these guys to be projections, right? Otherwise, this will never be multiplicative because these guys are projections. So the images must be projections also. And so Wang defined Sn plus and realized that it has defined it so it can act on this, and that action is ergodic. So that was kind of the first example of a genuinely quantum group acting ergodically on a classical space. And he even proved more. He proved that if G acts on Cn, if any compact quantum group acts on Cn, then there exists a map from Sn plus to G such that the action of G is just the action of Cn composed with that map. Right? So this means Sn plus is the biggest quantum group acting on Cn. So this leads to the following term. Sn plus is what we call the quantum automorphism group. Quantum automorphism group of Cn, or of endpoints, if you think in terms of spaces. But this is quite remarkable. And once we had this result, well, we can try to think, okay, so let's take other examples and compute their quantum automorphism groups, because this is a very nice example of a quantum group that's been studied from several points of view now, and it's really a beautiful object. So let's try to do the same thing for our other examples, and that's where things become a bit complicated. So now I have to, not only because I have to erase the board, which is kind of a challenge with this thing. Let's try to do it anyway. Okay, things become complicated because what could we try after this? For instance, we could try finite dimensional C-star algebras, like matrix algebras, for instance. And well, Wang tried it. And unfortunately, things don't work at all if you leave the commutative setting. I've spent 1 year in Germany. At the end, I knew how to use these things, but I'm a bit rusted now. So another theorem that Wang proved in his paper is that if you take any finite dimensional C-star algebra, which is not commutative, then there is no quantum automorphism. So why is that? The reason is not very difficult, is that if you have a quantum group acting on a finite dimensional C-star algebra, then it proves that the action must preserve a state. But then if you had a quantum group through which all the actions factor, then that one should preserve all the states. And well, the only way of preserving all the states is by acting trivially. So that's a kind of negative result. So finite dimensional non-commutative C-star algebras have no quantum automorphism. But then because, so I gave you the reason, it's because they have to preserve a state. So then you could say, okay, but now what about quantum groups acting and preserving a given state? If I fix a state, and then what he proved is you get a quantum automorphism group if you only look at actions preserving a given state that you fixed before. And so this led to the idea that maybe we should not look at quantum automorphism group of spaces just as such, but at quantum automorphism group preserving some structure on a space. So from then on, people tried different things. And one line of thought was to try to do this for classical spaces. Unfortunately, this led to essentially negative results. And that spawned a kind of a problem of its own, which is sometimes called quantum rigidity. There are lots of examples of spaces where there is no possible action of a compact quantum. So here are some examples of this quantum rigidity phenomenon. So for instance, if G acts, so you take a quantum group, assume it acts faithfully and smoothly on a compact connected manifold. So what does smoothly mean? I'm not going to give the definition, but basically, when you have a manifold, you have the algebra of continuous function. And of course, you have the subalgebra of C infinity functions, which is dense. So you want the action to preserve that subalgebra and to satisfy some density conditions with respect to the Fréchet topology on this. Okay. So if it acts smoothly and faithfully on a compact connected manifold, then G is classical. And that's the result of Goswami. So, okay, that doesn't work. Another example, if G acts faithfully and isometrically on Riemannian manifold with negative curvature, again, then G is classical. So here you see it's a bit different because so isometrically means that there is some relation between the action and the distance in the space. I'm not going to define this, but you can define in a very natural way what an isometric action is.
Question in the chat.
Yes.
Isometrically means isometrically with respect to the geodesic metric?
Yes. Yes, for a Riemannian manifold, it's with respect to the geodesic metric. Yes. So in general, if you have a metric space, you can define what is an isometric action of a quantum group in this. And here you take the geodesic distance, and then G is classical. So you see, you're not asking requiring the action to be smooth or whatever. It's really just an action on the underlying metric space, but you know the metric comes from a Riemannian structure with negative curvature, and then this is classical, and this is a result of curvature. And maybe a last one, which is of a bit of a different flavor. So almost all, with quotation marks, metric spaces have trivial quantum isometric group. So what does that mean? That means that you can define a topology in a suitable set of metric spaces, and that in the bare sense, you can prove some kind of genericity result for spaces on which no quantum group can act. Okay, so that's again curvature. So, and here, of course, I forgot something. You need the space to be connected. So the third one is a bit different in the flavor, but the first two ones, of course, one critical point is that the space is connected. So looking at this, Goswami started to wonder if there shouldn't be something more general, something like if you have a connected compact space, then no quantum group can act faithfully on this unless it is a classical group. But it's very hard to, yeah.
Classical, do you mean of the form continuous functions on some subgroup of?
Yes.
And another question, so when you, all the time when you're saying compact quantum group, you mean in the sense of these generators, these UIJs?
Yes.
Okay, right.
Yeah, I'm only focusing on that setting. So when I say quantum group, I mean the thing I defined before. And when I say classical, I mean it is, so it's just saying that the C-star algebra is commutative. And that implies that in fact, it's the continuous function on a closed subgroup of the orthogonal.
Right. So, thanks.
Yes.
Sorry.
Yeah.
And what happened for the non-connected case of Riemannian manifolds? For non-connected Riemannian manifolds.
Well, I don't think we really know what happens. You could have some. So you see, if you have something non-connected, then you could cheat. Like if the connected components are homeomorphic, you could just permute them or quantum permute them. using SN plus. So obviously you can cheat a bit in that case.
Okay,
so you
but
can build actions.
it's a trivial extension in some sense
Yes.
of what you
So what you can do is, for instance, if you take a connected space y and then you look at Cn tensor C of y. So this is the continuous function on n disjoint copies of y. So now you can take the action of Sn plus that I defined over there on this and the trivial action on this, and this gives you a non-trivial action on the whole space.
Sure.
So if the space is not connected, you can always cheat by just acting on the permuting the connected components, but not really acting on each connected component. Okay. So the general question is, can a compact quantum group act, say, faithfully, for instance, on a connected space? And Goswami asked the following question more precisely. He said, okay, so the idea is it's very difficult to study an arbitrary action, an action of an arbitrary quantum group on an arbitrary space. So here the point is all the time the action is preserving some structure. So that's what you use. This gives you this forces some relations on the generators of the algebra of your quantum group. And then you have to prove that the relations that are forced imply the commutation relation. But in general, you don't know how to do this. So he thought, maybe let's try for some specific quantum group and show that they can't act on any connected space, right? So you fix the quantum group. And the question is, can Sn plus act faithfully on a connected space? But something is, when you know a bit about Sn plus, you realize that, so faithful means there's no subalgebra like this, from which the action comes from. But in fact, for C of Sn plus, there is no subalgebra satisfying this anyways. So any non-trivial action is faithful. So the question is just, is there a non-trivial action of Sn plus? And the answer is yes. And that's a bit surprising in itself. And that's the answer which was given by Huang. So very briefly, what's the action? It's very simple. You take this. So you take n disjoint copies of a given connected space. So there's an action on this, okay, but the action, of course, is not. The space is not connected. But now what you can do is you take your n copies and you glue them over a closed subset. So you take Z in Y closed, and you look at the sub. So this is the algebra of functions on n disjoint copies of n of Y. And now inside this, you look at the subalgebra of functions such that for all, so this a function is just a tuple of functions, right? It's just given by n functions on Y. So you look at them such that Fi of Z is Fj of Z for any ij and for any Z in Z. Right, so you look at this. This is a subsystem algebra here. And you just check, and that's extremely simple to check, that this is stable under the action. Right? And now if you go through the Gelfand duality, this is exactly the functions on the space that you obtained by taking this and gluing over Z. Right? So you quotient by identifying all the copies of Z punctwise. I don't know, but that must fail somewhere. I don't know. I haven't thought about it, but there must be a failure somewhere. But at least if you just, work like this, you have an action on a connected space. So then Wang asked another question because he realized, any compact topological space, Hausdorff. And so Wang has the following question. So that action is faithful, but it's not ergodic, because if all the functions here are the same, then this is fixed, right? But this is not one. We take a non-constant function. So he asked, can Sn plus act ergodically? on a connected space. And what we do in one thing that we do in our paper is to prove that the answer to that question is no. So there's no ergodic action on a connected space. So how do we prove this? Well, we can't really use the usual tools for that because, well, we have no structure at all. Right? We're taking just an arbitrary space and we act on it. So we're going to use a different point of view. And we're going to go through some categorical machinery to understand what's going on. So what I mean by this is that compact quantum groups, they can be described in several different ways. And one way is that they can be seen as specific categories, or more precisely, as specific categories equipped with a functor. And because of that, you can think of any object attached to a quantum group as something that you should be able to attach to the corresponding category. And that works in particular for ergodic actions. And one can show that ergodic actions are the same as some specific functors on the category of representations of a quantum group. So let me just try to explain this quickly. So we have this U, right? We have G and we have this U. So this U is usually called the fundamental representation. Why is that? Because you have that map, which is exactly the same as the one I wrote before for S and plus, except that in general, of course, this is just a linear map, right? This is not a homomorphism, not algebra homomorphism in general, but it's a linear map. So this is exactly what's called a representation of a quantum group. So now if G is a classical group, what is U? Because it's given by the coefficient functions. So in terms of representation, it's just the inclusion of G in ON, right? Or in Mn of C. There's a definition of the group G as a group of matrices. So in particular, that representation, it's what defines the group. So it should contain all the information about the group. The question is, how can we make sense of that? How can we recover the whole group or quantum group out of that map? And the idea is we have rho, and now we can define its tensor powers. So rho n would go from Cn tensor n to this. And we'll send EI1 tensor okay to what we expect. We have the EJs here, and we have the corresponding product. So now I have these things, and the idea is to try to build a category out of these objects, right? Because for a classical group, when you have a representation like this, which is faithful, like the inclusion, then you know that any representation, any irreducible representation will appear as a summand in some tensor power. Turns out that the same is true for quantum groups. So we know that if we look at these guys, we can recover all the irreducible representations of our quantum group. So it's quite reasonable to look at these and to try to build a category out of them. And then the only thing that we have to do, if these are to be the objects in our category, is to find morphisms. And morphisms, well, we know how to define them. So if you have a map from Cn tensor m to Cn tensor m, we'll say it's an intertwiner if it does exactly what you may expect. That is, if you have rho tensor n composed with T, then this should be the same as T tensor identity composed with tensor n. So this leads us to the definition of something that I will denote by rep of GU. So that's a category with objects, well, the rho use tensor n, and morphisms being the intertwiners. And moreover, we have a functor on this, which is a stupid one, which goes from this to the category of finite dimensional Hilbert spaces. And well, you just send this to the space on which it acts and just do the identity on the intertwiners. They are already linear maps between these Hilbert spaces, right? So this FU is called a fiber functor. So in particular, this is, so in this category, you can do tensor products. Yeah. Yes, exactly. So this is a what's called a rigid C-star tensor category. So you have tensor products, you have dual objects of everything. And you have a functor, which is a unitary tensor functor. So it carries on the star structure and the monoidal structure from this to this.
Because up here, you've just got co-mod on modules.
Yeah, so what I didn't say, but it follows from the definition that these maps, in fact, are unitary for the obvious Hilbert module structures. So Hilbert space structure here and Hilbert module structure here. That follows from the unitarity of the matrix U. And so this means that you can carry on and get the C-star structure on the tensor category below. And so the theorem, so that's a version of Tanaka-Krein reconstruction for quantum groups. So that's a theorem which is due to Voronovich. So if you have a C-star tensor category with objects, the integers, and the unitary fiber functor from your category, shouldn't write it like this. Well, anyways, two. Then there exists the pair GU such that your category, in fact, is, so when I say is, I mean is isomorphic too. And F is just a few, right? So basically, C-star tensor categories with a fiber functor to the Hilbert spaces is the same as compact quantum groups.
The objects are the simple objects. Or
no, these are not. These are the tensor powers of rho U. So these are not simple in general. So the point is, you could do another version of this where you take all the irreducible representations, for instance, and so on. But the point is, you don't need. If you have this U and you know that its coefficients generate everything, then you can just look at tensor powers of U. So that's kind of simplification. You have less things to look at. Yeah, looking at some full subcategory of it, but which is generating in some sense. I mean, which is obtained from a generating object, more precisely. So now the nice thing is in there is that you have something smaller, but it still contains all the information. So now what about actions? Well, if you have an action, you would like to try to see it at the level of the category rep GU. And you can do this by trying to build a functor out of it. So how do you do this? Well, you see an action in particular is a representation, right? I said a representation is the same as an action, except that it's a linear map instead of a star homomorphism, but the star homomorphism is linear in particular. So I could just try to compare this as a representation to the representations rho U tensor n. So what I would like is to look, for instance, at AN. So an idea to compare is you take A, you make the tensor product as representations with Cn tensor some n. So here you're acting through alpha, here you're acting through rho U tensor n. And now you look at the fixed points of this. So that's somehow a way of comparing the way the group acts on this and on this, right? Basically, that's the points. That's exactly the part on which of A on which it acts exactly as rho U tensor n. So this is a sub algebra, and we know some facts about it which follow from general theory, which is that AN is finite dimensional, and the union of the ANs is dense. in A. And if T is an intertwiner, then, well, then T, so you can, if T is an intertwiner, you can look at identity tensor T here between this one and the other one. And it turns out that identity tensor T will again be an intertwiner. So you can bring it down to a map between the fixed points. So then T, then identity tensor T will send, say it like this, it will send, maybe I didn't write it in the right way, but okay, and then it's tensor T, so goes from CM, okay, it will send AM into AN. So this means I can build a functor on rep GU by sending rho U tensor N to AN, and then automatically I know where the morphisms go, right? This is compatible with morphisms. So this means that whenever I have an action, an ergodic action, sorry, I should have said that this is ergodic. So if it's not ergodic, things are more complicated. So basically, if it's not ergodic, you have to replace Hilbert spaces everywhere with Hilbert system modules over the fixed point algebra, right? So you have that fixed point subalgebra that I defined, and in general, everything lives in the world of Hilbert modules over that algebra. Okay, so now we have a functor, and what's the difference between the functor FU? Well, FU is a tensor functor, meaning that if you take two objects and you take their tensor product, then the image of the tensor product is the tensor product of the images, right? That's a tensor functor that respects tensor product. Here, that's not true anymore. So if you take elements in AN and AM, you can make that their tensor product, right? And it will be fixed. So it will live in AN plus M, but you don't get everything that way. So this means you have to kind of weaken your definition of a tensor functor. I'm not gonna write it down anyways. But. So what you do is, here's what you should be careful about. AN tensor AM, so you can send it there in AN plus M, but it's not surjective in general. Right? So all you have when you tensor two objects is an inclusion into the image of the tensor product, right? So you have a functor such that when you have two objects, you have an inclusion into F of alpha tensor B. That's what I'm saying. So that's not a tensor functor. That's a weak tensor functor. So basically, a weak tensor functor means for any pair of objects, you have an isometry like this. And these isometry should satisfy a set of compatibility relations, which are roughly the same as for a tensor functor. Don't write them down, but you can imagine them. And now here is the theorem we prove. So that's so I'm gonna call, yeah, I didn't give it a name, but okay, never mind. So if F is, so that's called a weak unitary tensor functor. On rep GU, then it comes from an ergodic action. Right, so you can build an ergodic action such that the corresponding weak unitary tensor functor is isomorphic to F. So now we have a description of ergodic actions in categorical terms. And what's nice with it? Well, it means now if you have a property of the algebra on which you act, this will give you some specific property that F must satisfy. But then you have a category. So you should think of a category as a kind of most like a ring or an algebra that you define with generators and relations. If you want a certain morphism to be definable on an algebra, then this means the generators must satisfy some relations, right? You have constraints. And the idea is to use these constraints to see that the constraints coming from the fact that the action is on a classical space, so that the system algebra is commutative, is somehow too strong and means that most objects must be sent to 0 by this F. So just a word on the proof of this. I'm not going to explain the proof. It turns out there already existed some versions of this reconstruction theorem, in particular one by Pinzari and Roberts, but their proof used a functor defined on all the representations of G, on the whole representation category. So the point of our theorem is that we just use a minimal piece of the representation category, and that's enough to recover everything. In particular, this gives us, from this, we can give a kind of explicit description of the algebra on which the quantum group acts by generators and relations. Okay, so now how do we use this to prove that you cannot act ergodically in a connected space? So of course, there is one space on which you can act ergodically. It's just one point, because that's the trivial action. It's always ergodic. Okay, but apart from that one, there's nothing. So how do you do? Well, you need a bit of representation theory of Sn plus. So the idea is, so you have this rough. So maybe just a word before. The proof of that theorem is nice, but that was not really our first goal. Our first goal in this work is that once you have this, then you can try to find new actions of quantum groups by just building tensor functors. And it turns out that the category rep GU for some families of quantum group G is a very tractable one. So these things are called easy quantum groups, and these are some for which we have a graphical calculus on rep GU. And that's a very nice graphical calculus based on partitions of finite sets. And so the idea is that you can just try to use it to build functors. So we build many families of functors, of quasi-tensor functors on this by just using this combinatorics of partitions. And then we know that this automatically produces families, several infinite families of ergodic action. Right? But afterwards, it's not always easy to try to identify explicitly the system algebra and the action in it, but at least this gives us many examples. Okay, now the other thing we can do, of course, is look at one particular case like Sn plus. And now the idea is that, okay, we have a functor here coming from an action. So we can extend it to all finite dimensional representations of Sn plus. Okay, there's a standard way of doing this. And in particular, we can make sense of it on all irreducible representations. And now we have to know what the irreducible representations are. So let me tell you what they are. This is a result of Bannica. The irreducible representations of Sn plus, you can label them by the integers in such a way that the number 0 is the trivial representation. The number 1 is the trivial is, sorry, 0 plus, so the trivial one plus the number 1 is rho u, the one given by the defining metric. And you have the following rule. If you take rho 1 and you tensor it with some rho n, then you get rho n minus 1 plus rho n plus rho n plus 1. Okay, so we completely understand the representation theory of that object. We know all the irreducibles. So now how do we work? Well, you see, for instance, so you can like do a little induction on this and get the following formula. If you take rho k tensor of rho n, then what you get is exactly the sum of rho I for all i's from k minus n to k plus n. Okay. So the crucial point here is that when you take two reducibles and you tensor them, any irreducible appearing here has multiplicity 1. Okay, so in particular, if you take rho k tensor rho k, then you have a unique copy of rho 2k inside it. Right? And no, that's not what I wanted to say. Anyway. if you take row 1 tensor K, then you have a unique copy of row K inside it. Okay, you can, that's easy to see. So there's a unique copy. And then now, if you take row K tensor row K, and you take an n which is between 0 and 2K, then you have a unique copy also, right? So now I'm going to denote by P n k k. So that's the orthogonal projection from the Hilbert space. So here is the Hilbert space on which this acts. So I define it exactly as the subspace of Cn tensor K corresponding to this one. And there is a unique orthogonal projection onto a subspace of this, such that here the restriction is rho n. And now here's the key lemma that we use. So assume you have an action on a classical space. Then if the image by the corresponding functor of, so how do I want to write this? Is the image of P and KK is non-zero, or n at least 2, then the range of P and KK is contained in an eigenspace for the flip map. So the flip map is just the flip map on HK, the one that swaps the two copies of HK. And the proof of that is not very difficult. So what we have is, we have a description. Once you have the functor, you can reconstruct the algebra. As a vector space, it's a sum of spaces indexed by the irreducible representation. And then the product is given by the decomposition of tensor products of irreducible. So now you take two elements corresponding here in the part corresponding to the representation number K, and you make their product. So this gives you a sum indexed by sub-representation. And then you make the product the other way around. This gives you another sum. But then the two products must be equal because the algebra is commutative. So this means the two sums are equal, but since they are indexed by irreducible representations, which are all different from one another, this means that for each n, the n component of one of your sum must be equal to the nth component of the other one. But basically, the two are almost the same, except that one of them is composed with the flip map. Right? So there is a kind of trick that there could be some scalars. So that's what we don't get that it's, I mean, we get that it's in an eigenspace, but not exactly that it's invariant under the flip map. But that's no big deal, because now all you have to do is to take n, k, and k and try to prove that the range of this thing is not contained in an eigenspace of the flip map. And you can do this explicitly because we have an explicit description of that projection, which is given in an old work of Moritz Weber and myself, using these partitions in this diagrammatic calculus. And so using this, you can prove that this criterion is never satisfied. So for any n at least 2, this thing must be sent to 0 by the functor. And now we are almost done. So we'll just try. I know I'm a bit late, but I started a bit late. So you'll forgive me for a few more minutes. Just want to give you the end of the proof. So if we have now our action, so we have the C star algebra A, commutative, on which we act. I explained here how we could write it as a union of ANs, but we can also do the same trick here, but using irreducible representations instead of tensor polars of rho. So then what you get is a direct sum of, so I call that AN, right? So you have a decomposition like this, and A is the direct sum is dense in A. Okay, and now let K be the smallest strictly positive integer such that AK is not 0. It must be 0. And what happens when you take an element in AK and you multiply it with another element in AK? Well, you get a sum, but each term of the sum will be given by one of these projections, Pn, Kk. But okay, they are all sent to 0 by the functor, which means there's no component for any n greater than 2. So this must be contained in A0 plus A1. Well, but A1, I mean, either A1 is 0 or it's equal to AK, right? Because K is the smallest thing. So in fact, this is contained in this anyways. But that means that A0, so call this B, plus AK, this is a subalgebra of A. And in fact, because the conjugate of any representation of Sn plus is equal to itself, you can deduce from this easily that this is even a sub C star algebra. And well, it's finite dimensional. But now a finite dimensional C star algebra always have a non-trivial projection. But when you look at the continuous functions on a compact space, a non-trivial projection means you have a connected component, which is not everything, right? So this means that X cannot be connected. So the only possibility if X is connected is that this thing does not exist. This means A is just A0, which is the fixed points. So this means you just have one point and you're acting trivial. So that's how you conclude the proof. And I'll end here. Thank you very much.
So, thank you for the nice talk. And is there any question or comment? Please.
From what you were saying, are we to assume that there's no quantum analog of the alternating group?
Yes. In fact, there are several results which tend to prove that there is no version of the alternating group in this Sn plus. Yes. So the consensus is that there is no quantum analog of this thing. Yes.
Okay, thanks.
Right. So is the graphical calculus that you mentioned related to the classical Specht theory of representations of classical Sn, like in terms of Young tableau and partitions?
No, not really. So it's not. So there are two things you can call partitions. They're the partitions you use in the Young tableaus and so on. So that's like decomposing an integer in a sum of integers. But here by partitions, I really mean taking a finite set and looking at a collection of disjoint subsets whose union is everything. And no, it's not exactly the same because here we only use partitions which are called non-crossing. So this is in fact much closer to the combinatorics of Temperley-Lieb diagrams. In fact, this is a kind of variation of the. So if you look at the intertwiners between row tensor n and itself, this is a kind of variation of the Temperley-Lieb algebra. So yeah, it's very close to Temperley-Lieb combinatorics rather than Young tableaus. Well, so the results that I mentioned for quantum rigidity here, this is, in fact, I should have said it, this is true for, they don't assume such a thing. This is for arbitrary quantum groups. Yeah, so here I focused on Sn plus, so that's why I wanted to have this simpler setting. But this is more general. In fact, in general, the compact quantum group will be a projective limit of compact matrix quantum group. In the same way as a compact group is a projective limit of compact Lie groups. So if you have compact quantum groups that act nicely, then you must have compact matrix quantum groups acting nicely also. So if you understand these ones, you already know a big part of the problem.
We have some question from the chat. No, sorry. Branimir has a question.
Thank you. So two questions. First, with regard to those initial that initial list of rigidity results, there was in particular the results of Alex Gavasito about metrically isometric actions on Riemannian manifolds with negative scale curvature. But are there any results about merely metrically equicontinuous actions? Not
that I know of.
Okay.
Not that I know of. But,
Okay.
Okay. I'm not totally an expert in these quantum rigidity things, but I haven't seen anything in that direction. So far, already understanding isometric action is. So the thing is, it's not. Yeah, at least. Well, no, that's not exactly the same. Yeah, no. For equicontinuous actions, I don't know of any results so far. Okay.
Okay. The other one's just a really silly philosophical question. So I guess it's pretty obvious that Sn plus is not, I guess, it's not a it's not dual. It's not a discrete quantum group, but it's not dual to a discrete quantum group.
It's dual to a discrete one. Yeah.
It is dual to a discrete one.
Yeah.
Okay. So in that case, I mean, so if you sort of go into the opposite regime to an ergodic action, think in terms of something like a free action. I mean, if we want to pin down what a Galois, like a Galois cover is with quantum deck transformations given by something Sn plus, like, is there any insight into what that would mean beyond just having a Hopf-Galois extension or a free action in the sense of Elwood?
So usually free actions for compact quantum groups is understood as a kind of Hopf-Galois condition. Yeah. So that's, but maybe one thing is, so I think which maybe comes close to what you're meaning. So there are some natural open questions following this result. So the first one is, on which space can Sn plus act ergodically? We know only one space, it's endpoints. Are there others? I mean, one points and endpoints, and that's, are there others? Or for instance, can it act on a Cantor set or something like this? Mm-hmm. And the other question is, in general, if it acts on a space, not connected one, what does the action look like? So you have this example of Wang for a connected one. The idea that you could, so the idea is you could look at the fixed points. So this gives you a quotient of your space. And so you have your Sn plus acting thing, you have a quotient onto the fixed points. And what are the fibers, for instance? Should there automatically be a kind of bundle structure that enables you to reconstruct the big space from the small one on which Sn plus acts trivially, like a base? I don't know, but the thing is you can define some kind of, you can somehow understand the fibers because you have a notion of orbit and the action on the orbits is ergodic. So if you manage to classify ergodic actions first, then you know what the orbits must be. And you can hope that, for instance, the orbits, if it's a finite number of points, that number should be constant on connected components, for instance. And then there's a hope that you could really reconstruct the whole action through a kind of, of bundle structure or something like this. So I don't think there's anything known on this, but that's kind of natural question, next question from this result.
Thank you.
There's a question in the chat. Is there a Cayley type theorem for quantum groups?
It's very tricky. So the short answer is no, in the sense that a finite quantum group is just one whose sister algebra is finite dimensional, of course. And no, they don't embed into this Sn plus, not necessarily. And for the reason that you also have, as I said, when you have a finite dimensional sister algebra, you have a quantum automorphism group of this if you fix a state. So now if you have a finite quantum group, it acts on itself, right? And it preserves its Haar state. So it always embeds into the quantum automorphism group of the underlying finite dimensional sister algebra, preserving that Haar state. But this thing is not the same as Sn plus. And now there are explicit examples where we prove that there is no possible embedding into Sn plus for such things. So there's no Cayley theorem in the sense that they do not always embed into this, but then they always embed into a kind of different version of this for non-community finite dimensional C-star algebra.
Do we have any more questions?
Do you have some kind of uniqueness in your theorem? Like, can you really reconstruct the action from some concrete data?
Yes, yeah. So we have a uniqueness in the theorem, and we have an explicit description. I mean, explicit.
And so if I understand this correctly, I mean, what exactly do you have to specify? If you want this weak tensor functor, you probably need to know the algebra beforehand where it is supposed to act, or
no, you don't need. And in fact, what we do is we construct many actions by really just specifying the functor itself. So we build. So what you need is you build a family of Hilbert spaces with isometric embeddings between the tensor products, right? So Hn tensor Hk should embed into Hn tensor K. So you have to find embeddings which compose in a natural way, and then you have to build a functor.
Yeah. Okay, I see. So you have those ANs as vector spaces, but the algebra structure cannot be seen by the functor, so you don't have to specify it.
So then it will be given by the. So the algebra structure will be given by the intertwiners. I mean, by the images of the intertwiners, if you want, of the category. So basically, because you know what I mean, we build lots of functors by taking spaces which are spanned by partitions. We take partitions, we formally span spaces with them, and then define a Hilbert structure, which is the usual one. And then all you have to do is to construct the functors. So make sure that when you apply your morphisms, which are given by partitions, again here, it acts between the correct spaces on both ends, and then you get the result. But in many cases, we're not able to give nice description of the C-star algebra. In some cases, we can, but in most, we don't really know what happens.